Capacitors are devices that store electric charge. A capacitor essentially consists of a system of two conductors close to each other and separated by an insulating medium. The conductors can be of any arbitrary shape. Generally, the conductors are given equal and opposite charge of magnitude Q. This can be done by connecting them to the two terminals of a battery. The conductors carrying the charge are referred to as the plates. And because the plates are charged, an electric field of strength E exists between the plates. The potential due to the plate having excess positive charge plus Q on it is V1. The potential due to the plate having excess negative charge minus Q on it is V2. The positively charged plate is at a higher potential than the negatively charged plate. Therefore, V1 is greater than V2. Hence, a potential difference exists between the two plates. Let the potential difference between the plates be V equal to V1 minus V2. As potential difference is measured in volt, this potential difference is referred to as voltage. We see that the total charge on the capacitor is plus Q plus minus Q equal to 0, as the conductors have charges of equal and opposite magnitude. It is a common practice to refer to the magnitude of charge on the conductors as the charge on the capacitor equal to Q, and the potential difference between the plates of the capacitor as the potential of the capacitor V. The electric field strength in the region between the plates increases as the magnitude of the charge on each plate of the capacitor increases. Then, the potential difference between the plates also increases. Since the potential difference V between the plates increases linearly with the charge on the capacitor, Q and V are proportional. Hence, the ratio Q by V is equal to C, where C is a constant, which is the capacitance of the capacitor considered. Let this be equation 1. Capacitance C of a capacitor is its ability to store electric charge. Greater the capacitance C of a capacitor, greater is the charge it can store, and hence greater is the electrostatic potential energy. The capacitance C depends on the size, shape, distance between the plates, and also the medium between the plates. The SI unit for capacitance C is the ratio of SI unit of charge to SI unit of potential difference, which is Coulomb per volt. It is also referred to as farad, named after the English physicist Michael Faraday. Generally, the submultiple units of capacitance like microfarad, nanofarad, and picofarad are used in practical applications than farad, since farad is a measure of higher magnitude. The capacitor in which the value of capacitance can be changed is called a variable capacitor. The symbols for a capacitor and a variable capacitor, as used in circuit diagrams, are as shown. It is important to note that a single plate can also act as a capacitor assuming that the other is at infinity. For a capacitor having a very high potential difference between its plates, there exists a strong electric field between and around the plates. This strong electric field can ionize the surrounding air. The charges, so produced due to ionization, accelerate towards the oppositely charged plates of the capacitor and neutralize the charges on the plates of the capacitor, at least partly. Hence, we can say that the charge on the plates of the capacitor has leaked away due to the reduced insulating power of the intervening dielectric medium. When a sufficiently intense electric field is applied, the electrons of the intervening dielectric medium are torn away from their parent atoms, and the dielectric medium behaves as a conductor. This phenomenon is known as dielectric breakdown. Dielectric strength is defined as the maximum electric field strength that a dielectric medium can withstand without a breakdown of its insulating property. If the intervening medium is air, then the corresponding dielectric strength is 3 × 10⁶ volt per meter. If the distance between the plates is dr equal to 1 centimeter or 0.01 meter, then the corresponding potential difference V can be obtained by using the relation V is equal to EdR. Substituting the values of the above parameters, we see that V is equal to 3 × 10⁴ volt. Thus, we see that for a capacitor to be able to hold a large amount of charge Q, its capacitance has to be large enough so that the value of the potential difference V between the plates does not exceed the value of the potential difference and the electric field strength values corresponding to the dielectric breakdown. This means that there is a limit on the amount of the charge that can be stored by a given capacitor for a given intervening medium, without dielectric breakdown taking place. We also see that from the equation 1 that when the capacitance C is quite large, it can hold large charge Q at a relative low potential V. Since C and V are inversely proportional, the capacitors are used not only for storing charge, but in other applications as well. Some of their other uses are to tune the frequency of radio receivers, used as filters in power supplies,